Yeah, so dear students, so let us start today's lecture. So this is MA415 Algebra lecture number 27. Okay. So now recall that we are discussing about unique factorization domain in our last lecture. Okay, and we have given proof that inside the unique factorization domain, you know that prime element and irreducible elements are same. They are same element, right? So naturally there is one more such kind of ring which has natural properties of ring of integers, and this kind of ring are called principal ideal domain. So let me start with that today. Principal ideal domain. Okay, and we generally call this as PID. PID. Okay. Now, what is the definition of a principal ideal domain? So, I mean, as the name says, so an integral domain is said to be the principal ideal domain if every ideal is principal ideal. So what does that mean? That means every ideal is generated by a single element, right? This is the meaning of principal ideal. So principal ideal domains has this beautiful property. Whatever you choose the ideal, and no matter how many number of element you choose to generate, there will be always a single element that generates the full ideal. Okay. Now the natural example, obviously examples. Okay, so the most natural example is the ring of integers. Okay, and ring of integers is principal ideal domain. And why so? I can just give you a short proof. Whatever you choose, for example, let me start with two elements. So let you have two elements A and B belongs to Z, and consider the ideal is generated by A comma B. Okay, so now I would like to see that there exists an element which also generates this whole ideal. Okay, and what is the element? So this element is called the D, the GCD of A and B. Generally we write down by these symbols. Yeah, so this is application notation, maybe both the same symbol. Okay, so the GCD of D, actually they generate the full ideal. Okay, so what does that mean? That means this ideal generated by D is nothing but I itself. Okay, now how to prove this kind of statement? Yeah, so one can see there are this is in fact, I need only the property the integral domain, then I can give a proof. So let me give a short proof. In fact, this is not a special case of R. For any if you choose any principal ideal domain, if you choose any such elements, so the GCD will generate the full ideal. Okay, in particular it is true for Z also. So so what does that mean? So you see that Okay, so I need to prove that GCD is this. So the property of GCD, you remember the property of GCD of AB, that using Bézier lemma we prove that you can write down G as some K1 into A plus K2 into B, right? And so what does that mean? That means D belongs to, see, this is an element of ideal generated by A, this is B, so this belongs to I, right? So this is something belongs to I, right? So what does that mean? That means this ideal generated by D is a sub-ideal or subset of I, right? One part is obvious, other part is also same. Conversely, you see A can be, so what is A? So A will be something like D times A1, right? Because D is a divisor of A, right? And what does that mean? That means this implies that A belongs to the ideal generated by D, right? And similarly, say B equal to D times B1, and that will implies that, so let D be the GCD of A and B. Let me mention that, and that implies your B is also element of these. And once you know A and B belongs to that thing, then the I, which is the ideal generated by A and B, that is also a subset of this, and then they're equal, right? So you have an element which is the greatest common divisor that will generate the full ideal. Okay, so in principal ideal, so Z is a principal ideal domain, and in fact it is true for every principal ideal domain. In every principal ideal domain, you find out the GCD exists, and that the generator of that ideal generated by any n number of elements. Okay, so this is a very important property. Maybe I can show you, I can give you something which is not a principal ideal domain. For example, example 2 that we discussed for unique factorization domain also last day. Let me discuss here. So my ring is that Z to the minus 5. Okay, and you see that this ring is not a principal ideal domain. Why so? Because see, I mean, there are many ways to prove that. So you find out that the two ideals, so that I1 it is, say, for example, 3 comma 1 plus root 5. Okay, this is not a principal ideal domain. They are not a principal ideal. You cannot generate a single element which generate these ideals. Okay, because you cannot define the GCD in this ring actually. Okay, so similarly, you see another ideal, and this is also the 3 comma 1 minus 5. Okay, and you see that this is also not a principal ideal, so this is not a principal ideal domain. Okay, maybe one of the most important example I should say that you take ring of integers and then polynomial ring over that. Okay, and with respect to the addition and multiplication of polynomials, now we find out that this is also not a principal ideal domain. For example, the ideal I, for example, is generated by say 2 and x is not a principal ideal. Okay, now how do you prove this is not a principal ideal? Yeah, so the proof is simple. So on the contrary, let us assume that um, I is generated by a single element, some fx. Okay, and so what does that mean? That means I'm saying that this is the same ideal. Okay, now if this is the same ideal, then that implies that first of all you can write down fx. Fx belongs to this, right? You can write down fx in terms of 2 into some f1x plus some x into some f2x, right? This is one obvious expression. And also 2 divides 2 belongs to this ideal, so so what does that mean? 2 will be this is 1, and then this is one expression, then you have many more expression. If 2 belongs to this ideal generated by fx, and that will implies that 2 will be some fx time some gx. Okay, so that will force this will force that your fx must be a constant. Okay, this must be a constant, and if fx is a constant, then what happens? Then you cannot generate x, right? So this will force that fx is a constant polynomial, and thus x cannot belongs to fx, right? So in any way, whatever you assume this expression are there, you can easily find out that there is a contradiction. You cannot do it. Okay. See, these polynomials, the invertibility of polynomials is difficult here, right? Because they are integers, right? Okay, so the question is that what happens if you change it? If you change it by instead of integers, so what if a field, say, okay, r equal to fx, where if be a field. Okay, so in that case, actually the answer is yes. Fx is a principal ideal domain. In fact, it is more than principal ideal domain. That we will prove when I will discuss something called Euclidean domain. Okay, but just take it as an example. It is for a field. It is always possible that ring of integers, ring polynomials over the field, they always forms a principal ideal domain. Even they form something called unique factorization domain. Okay, so these are the example you record we will give proof in upcoming lectures. Okay, now what important property we know? Let me discuss some of the properties. For example, we discussed that in UFD the prime element and maximum element are equal. They are prime if only the maximum element. But in the ideal level, what happened? Let us try to understand. So, for example, whatever you do in this integral domain property, then this maximal ideals always prime ideal, right? So that we know. So in any integral domain, this maximal ideals are prime ideals, right? That we know already. We have proved these things. But we can ask the converse statement that whatever the converse, and I have given a example that converse is not always true, right? Prime ideals may not be maximum ideals. Okay. Now conversely, converse thing is true for something called PID, and then the theorem is that in this case, so I'll give a proof immediately. Okay, so in a principal ideal domain, every non-zero, obviously zero cannot be a maximum ideal, right? Every non-zero prime ideal is also a maximal ideal. Okay, so this is a very important theorem, and you see the powerfulness of the principal ideal that force to have all the primes becomes prime ideal become maximum ideals, right? Now, how do give a proof of this kind of statement? So the proof is not difficult, and we only use 2-3 properties. Okay, so what you need to prove? You need to start with a prime ideal, and so let me start. So let I be a prime ideal in, say, R, which is a PID. Okay, now as R is a PID, then you know that then I is generated by a single element, right? For some P belongs to R, right? The principal ideal property tells you that this happens. Now, also we proved that I think 2-3 lectures before that in any integral domain you have a nice property. What is the nice property? That whatever ideal you choose, that will be always contained in some maximum ideal, right? So let M be a maximum ideal. So this need not be unique. There might be more than one maximum ideal containing P. So let M be a maximal ideal of R containing P, right? This theorem is already proved. This ideal P, I or whatever given by P. Okay, so every ideal is sitting inside the maximum ideals, and you choose the maximum ideal same. Okay, but what is the advantage here? Advantage is that your ring is principal ideal domain, and hence this maximum ideal can be also written as a generated by a single element, right? So thus you have M that is generated by some elements, say small m, for some M belongs to R. Okay, so this maximum ideal is generated by a single element, say small m, and you can write down this is a principal ideal. Okay, now you see that you have two principal ideal, one is sitting inside another one, right? So you have this statement that this ideal generated by P is sitting inside ideal generated by M, right? Now what are the possibilities here? See, I mean, either they are proper or it can be same also, right? So what are the proper? So this implies you can always say that your P, the prime ideal P, is inside. The prime P is inside that this ideal, right? And thus, what you have, you can write down P in terms of multiple of M, some M into M dash, right? For some M dash belongs to R. Okay, so far so good. So you started with the prime ideal, which is generated by element P, and because it is contained in a maximum ideal, you find out that there exists an element M with this property P equal to M into M dash. Okay, now with the help of this property, what you can now say, you can say two things. The one thing is that either, so there are two possibilities, right? This you see P is this is prime ideal. So if now. Okay, let me write down now. You see that p equal to m into m dash, that is the element of a prime ideal, right? This prime ideal, right? So by using the property of prime ideal we have what we have. So if the product of two elements belongs to a prime ideal, then at least one has to belong to the prime ideal, right? So we have either m belongs to this or m dash belongs to this, right? Okay, now can it be n dash belongs to p? I mean, I don't know. Let us see. So if what happens if m dash is an element of this ideal generated by p, then m dash will be multiple of p, right? So then m dash will be something p times some p1, right? So what do you have? You know that already your p equal to m dash, so you can use that. So p equal to m dash, and that will gives you that um, m into p into p1, and hence this will see. I think yeah. So IBA, see, this is PID is given, right? So what does that mean? PID means it's also integral domain, right? Now if you use integral domain property, that will gives you that m into p1 equal to 1, as R is an ID, integral domain also, right? Or, I mean, let me write no PID are also IDs, right? So what does that mean? That means this implies m is a unit in R, and so when you have a unit, then what happens? Then the ideal capital M is generated by the element small m is actually the full ring, right? This also we proved that whenever you have an element which is a unit, then the ideal generated by that element is becomes the this becomes the full ring. Okay. Okay, so so far so good. So but this is a contradiction, because m is a maximum ideal, right? So this is a contradiction to the maximality okay maximality of m, right? So maximum ideal cannot be the full ring, this has to be a proper ideal. So then what is the option? So you have two options, one option cannot be possible. So what is the other option? Then you have m belongs to this ideal generated by this, and this implies that capital M, which is a something of this, right? But you know already the other way around. You know that this M contains this ideal generated by P, and this implies that M equal to P, M equal to I, which is generated by P, right? So what does that mean? That means thus I is a maximal ideal. Okay. So this is the shortest and sweet proof of the fact that in principal ideal domain, prime ideals and maximum ideals are same. non-zero prime ideal updation. Non-zero prime ideals are nothing but the maximum ideal, if and only. Okay. So so in particular, you can for example, you see that inside ring of integers, whatever you ideally choose generated by prime, they are prime ideal, right? So they are all also maximal ideals. Maximal ideals. Okay. If you choose a prime and the generate the ideal, they become maximal ideals, right? And you know also the characterization theorem, whatever we proved, that Z mod this is actually field, and this is we call Z mod this, right? It's a field also. Okay, you can also think from this side. Okay. So so this is this important theorem, and then this theorem also tells you, we can also tell some more important things from this theorem. You can also say that this prime elements, I just proved that prime ideals are maximum ideals, right? But it is also true that prime elements are irreducible element. So let me give the proof of that. So theorem, so let R be a principal ideal domain. Okay, then a non-zero element in R is prime if and only if it is irreducible. That all it is. I hope you remember the definition of irreducible. It was only the last class we defined it. Okay. So yeah, so one part is obvious. So can you say, remember what is the part? We already proved that in the last class that whenever you are in an integral domain, then prime element are always irreducible element, right? So one part is obvious. So proof. So these primes are irreducible in any integral domain, right? So in PID also. Okay. So the natural question is that what about the converse? That if you start with an irreducible element, does that also a prime? And we will show that it is actually indeed a prime number. Okay, prime element. So conversely, so you start with, say, let R be an irreducible element in say R. Okay, now I need to show that R is a prime element. So what does that mean? That means if R divides something, then either R divides one of them. Okay, now concern, let say R divides AB for some A and B belongs to capital R, the ring. Now what we need to say, we need to find out that either R divides A or R divides B. Okay. Now so this is given to me. So now I consider this ideal I, which is ideal generated by the element R. Okay, and mm, mm, this is my ideal. We generate the picture generated by I, and M be a maximal ideal containing I. Okay, that is always possible. So we can have maximal ideal that contains I. Okay, and now as R is a PID, principal domain, we know that M can be generated by single element, right? For some M belongs to R. Okay, so what does that mean? That means you can say that this I is a sitting inside M. So what does that mean? That means the ideal element by P is sitting inside ideal element by M. Okay, clear? This is okay to everyone? Okay, so now straightforward you can say from here that this okay, so you can say that the P is an element of the ideal element by M, and this implies P can be written as some M into M dash, right? Now if P can be written as some M into M dash, then what happens? Then either okay, so one more thing. See, this element P is a prime element, right? So that tells you that this is a prime ideal. This is also important observation. So that, or yeah, so what is, no, this is not P, this is R actually. So R is a prime element, right? So as this is a prime ideal, because prime element is prime ideal, what happen? And then either M belongs to this or M dash belongs to this. Okay, at least one of the thing must happen, right? Now M dash cannot be belongs to R dash, that we already proved. That will give you contradiction to the fact that M is a maximum ideal, right? So M dash cannot belongs to ideal generated by R, as earlier so we already show that thing is not possible. Okay, so M belongs to R, and M belongs to R tells you that implies that capital M is inside this. Okay, and which is I, so that means that they are equal, right? So if they are equal, that means okay, so now I think we have 1 minute. Yeah, I think I have missed one property that I need to use here. This is I need to prove this prime ideal. Okay, no, I think this part is not true. This is I need to prove. This is I need to prove, right? So far it is okay. And now I need to assume that, because I assume that R is irreducible element, so I need to use that property that I did not use it. So let me use that thing. So this is not also true. Yeah, this property I missed it, right? So what was the assumption? Assumption was that R is an irreducible element. Yes. So R is an irreducible element, that I need to use it somewhere. Okay, so I think this is okay. Now because R is an irreducible element, and if you write down R in terms of product of two elements, then either of them has to be unit, right? As this is the yeah, as R is irreducible, yes, that proves the other one which I already proved it. Then either M or M dash is unit, right? This is the definition of irreducible element. Yes. Yes. So now can M be a unit? No, right? Because but M cannot be a unit, right? So M cannot be unit means what? So that means if M is a unit, then it is maximum idea, right? So this will be the whole thing, right? Not possible, right? So M dash has to be unit. So R will be associated to M, right? So what are the M also? If M is unit, then also you can say, but then in that case it will be the full ring, right? So thus there are two choices. Either this ideal is the full, this maximum ideal, or M is the full ring. All right, full ring. This is the only choices you have. So what does that mean? That means the ideal R is also prime, it is maximum ideal, right? Because if it contains in the maximum ideals, then it has to be equal to them, or the maximum ideals is nothing but the whole ring R. So what does that mean? That means R, ideal generated by R, cannot contain properly in any other ideals, okay, in any other than M, other than itself and the full ring. And this is the proof saying that thus this ideal generator R is a maximal ideal. Maximal ideals. Okay. Maybe the maximal ideals implies that this also prime ideal is also prime ideal, that I already proved it. Okay, now if R is a prime ideal, then done. Because what we need to prove? We need to prove that R divides AB, then at least one of them divides AB, right? So now you use that fact that now as R divides AB, you have what you have. You can write down AB equal to some R time R dash. So this implies AB, the element A into B is a element of the ideal generated by R, and thus okay, so I mean thus here. So now because R is a prime ideal, so this implies A belongs to R or B belongs to R, as R is a prime ideal. Yeah, this is the proof. Okay, so we just proved that. We just proved that it is always not possible to it is always the case that inside a principal ideal domain, the prime elements are also, and the irreducible elements are also prime element. Okay. Okay, so yes, so this is the end of the proof. Okay, and now we are going to discuss one very important theorem, which is natural question. We remember in last lecture we saw that inside an unique factorization domain also primes and irreducible are equal, right? and now you also prove that inside the principal ideal domain also this is true, right? So the natural question to ask, what is the relationship between these two ideas, whether one is implies other or other is implies one, first one. Okay, and this is the very fundamental theorem, and that tells you that theorem that every principal ideal domain is also unique factorization domain. Okay, so whatever the property that enjoyed by UFD, they also that property should be also satisfied in PID, right? Because PID is a UFD, but converse is not true. So there might be UFDs which are not PID. That is possible. But if you have a PID, that must be an UFD. Okay, unique factorization domain. Now, how do you prove this kind of important theorem? So let me give a proper proof. Okay. So you need to prove that in a principal ideal domain, every non-zero non-unit element has some finite unique factorization with irreducible element, right? And this unique factorization means that the number of irreducible terms are finite. Okay, so how do we prove? So let R be a non-zero element in so PID say R, capital R, in R. Okay, so you have a non-zero elements in R, and then you need to check whether this is factors or not. So what are the possibility? I mean, I can also assume that non-unit non-zero and non-unit, because then otherwise nothing to prove, right? If it is unit, then it is done. So okay, so what are the possibilities? The possibilities can be that R can be irreducible itself, right? Then done. So if R is irreducible, then we are done, because that is the only factorization of R itself, right? If not, then what happens? So you can further break into smaller product of irreducible element, right? So if not, then what you can do, then R can be written as something, say R1, R2. Okay, and with neither of R1, R2 unit. They cannot be unit, right? If they are in one of them is unit, then that is R1 or R2 has to be associates of R. But then that is okay, right? Associates generate the same ideal, so you don't have to bother about that thing. Okay, so if R is not a irreducible element, so you can break into smaller elements which are not unit. Now there are again two choices. Now for R1 also you can argue the same thing, whether R1 irreducible or not. So if R1, R2 are irreducible, then we are done, right? This is the term which started here. If not, then you can also say further write down R1, something some R11 and say R12, something further. Okay, and so on, right? So what that means? That means you are getting a chain of ideals, right? So you're starting with R, and you see the R is contained inside R1, okay? And I mean, this cannot be same. This is a proper ideal because neither of R1 R2 is the unit, right? So the proper ideal. Similarly, R1 1 and so on, right? This is going on and on and on. This is all are proper ideals. Okay, so what does that mean? That means you are getting, if this process does not terminate, then you are getting a infinite chain of ideals. Okay, now I will prove that this cannot be possible. This is a contradiction inside a principal ideal domain. Now why this cannot be possible? Okay, so claim. So my claim is that in a principal ideal domain, every ascending chain of ideals, for example, say I1, I2, and dot terminates. What does that mean? That means after a certain stage, that is, there exists an n such that this in is actually equal to ik for all k greater than equal to n. After that, everything same. Okay, and this property is called ascending chain property, is in PID. So this is very important property. And okay, maybe you will learn something when you learn some commutative algebra. There is something called Noetherian. This is called Noetherian property. The ascending chain terminates. Okay, so okay, so how do you prove this statement? If we prove this statement, then we are done, because we said that if it is, this process does not stop, then you will find a infinite chain, right? But I just want to prove that infinite chain cannot exist inside a PID. Now how to prove this statement? So you write down, say, I, the union of this ascending chain, I j, you have to say 1 2 whatever. Okay, so this is an ideal, right? Because this is all are inclusive. So so this is then I is a principal ideal in R, right? Because R is a principal ideal domain, so I is also principal ideal. So what happens? So that means, thus your I is generated by a single element, something say X, right? And this is also union of, say, this whatever ij's ii's. So there exists, so that means, and there exists some n belongs to natural number such that X is an element of In, right? Because X belongs to the union, and hence X has to be one of the set. So what does that mean? That means on the one hand, there are two things. On the one hand, your In is a sitting inside capital I, which is the union, but capital I is generated a single element which is also sitting inside In, and this implies that your In is nothing but the whole union I, right? And done. So once In is whole union I, then whatever you take the ideal, because that has to be equal to I. So In equal to Ik for all k greater than equal to n. Okay, so my claim was true, that ascending chain of ideals determinates inside the principal ideal domain, and hence whatever I am discussing, this kind of infinite chain cannot possible. So thus this process must terminate somewhere. So we will have finally many irreducible elements will only occur, right? So thus, so Thus you can write R equal to something, say P1, P2, something, say Pn, okay, for some Pi's irreducible. Okay, now we need to prove other part, the uniqueness property. um, Now to prove uniqueness property, so see, initially I assume it is non-zero non-unit, so n has to be at least bigger than 1, bigger than equal to 1, so this is given n greater than equal to 1, right? Now let there exists another presentation, say p1 equal to p2 pn, and then say q1 q2 qm. Okay, then what happened? Then you can use the division algorithm part. So you see the p1 divides this whole thing, so p1 divides q1 q2 and qm, and once p1 divide this product of irreducible elements, then what happens? Then p1 has to divide, like there will be one element which will be associates of p1, right? Some associates of p1. This is the property of unique factorization domain, right? This is the property of unique factorization. So p1 has to be divides one of those qi's. So what does that mean? That means there exists. Okay, so so if possible, I can number these qi's and such that we should write down without loss of any generality. So let your p1 equal to some u1 time q1, some unit time q1. Okay, so what does that mean? That means you can replace now p1 in terms of u1 q1, and then you can cancel out q1 because this is the integral domain, right? You can have cancel property. So thus you can write down that r equal to u1 q1 p2 p3 pn, and then q1 q2 qm, right? And then you can cancel this as we are in an integral domain, PID as integral domain also. So what will happen? Then we'll have u times some p2 p3, okay, and so on. So see, there are two possibilities that n can be bigger than equal to m also, right? So it's also possible. And so I'm assuming that n is less than equal to m, but if we assume m is less than equal to n, then you can do the other way. You can write down q1 in terms of unit time p1. It's always possible because units are invertible elements. You always have inverse there, so you can multiply by the inverse. Okay, so you can find out this p2 and then p3 and then pn, and that will be equal to q2 q3 and something qm, right? Now you will do the process again. Now p2 is also irreducible element, and that also divides this q2 q3 qm. So that means one of those qi's will be associates of this, right? Now you apply the same process again and cancel it out. If you cancel it out, then what happens? Your number will become less. So after n many stage, what happens? After n many stage, you will have some q n plus 1 to qm, and that has to be equal to some u1 times u2 times some units. These are all units, right? So what does that mean? That means these elements are only units only. So these are all units. So this cannot be irreducible element, right? Any irreducible element has to be non-unit, right? So thus you will have m equal to n, and not only m equal to n, you have a unique representation. You just prove that your pi's will be some multiple of that, right? So this completes the proof. Okay, so what we just proved, we proved that in a UFD, every in a PID has always UFD. So the property whatever is true for an UFD is also true for an PID. Okay, maybe I will stop here my lecture today. Tomorrow maybe we can discuss little more about PID. Okay.